RC coupled common emitter amplifier. Now here two transistor RC coupling is applied. Now the two transistors are Q1, Q2 and 4 resistor biasing network CE bypass capacitor across RE. Input signal 811 Q2 transistor 4 bias network again. And here is the capacitor that is called the coupling capacitor. So R1, RL, RE, R2 4 bias network, again bypass capacitor. So this is the arrangement. Output signal across 3 and 3 VCs is applied. Coupling capacitor C. So we to analyze low frequency to this circuit, how this circuit responds to the low frequencies. And what is the effect of the coupling capacitor C? This is very important. There is another capacitor which is across the RE, that is named as CE. What we are doing? We are doing this bypass capacitor, the capacitance as infinity. If the capacitance is infinity, the reactance becomes 0, because this is RE, here is a bypass capacitor CE, because XC equals to 1 over C omega. If CE tends to infinity, then this reactance tends to 0. That means a short circuit across RE. If short circuit, then there will be no role of RE, because all of the current will pass through the short circuit. Thus there is no role of RE from the equivalent circuit. We will not show now RE in the equivalent circuit. And second, R1 and R2, the biasing resistor has been so designed to be very, very large as compared to the input resistance. And if they are made very, very large, what happens as compared to the input resistance? So because when the resistances are in parallel, one is low and one is high, the parallel combination come closer to the low value, not that of the larger value or higher value. So if R1 and R2 are higher, they are neglected as compared to the input resistance of the transistor. So we neglect the bias network in the equivalent circuit again. This is a current generator GMVBE1. This is RL. This coupling capacitor. Now HIE second transistor. Now here VBE2 at the port number 2 and 2 at Q2, VBE1 at Q1. Now there are two loops here. In one loop the current is GM into VBE1, another loop the current will be I2. So the coupling capacitor, the main important is, because omega is low, this reactance will be high. So if the reactance is high, we cannot ignore its effect. We cannot, it cannot be treated as like a short circuit. So we have to consider the capacitance of the coupling capacitor C. Here the current flowing is I2 in this loop. In this loop, GM into VB E1. Now current flow like this. So let me write the Kirchhoff law in the closed loop. I2 HIE 1 volt is. Now XC is 1 over C omega and C into 2 pi F. So S is equals to J omega. The reactance becomes I2 into 1 over SC. Remember, S is equals to J omega. Now let me write the equation again. I2 into HIE plus I2 into 1 over SC, the voltage across the capacitor. Now through RL there are two currents, but they are opposite in direction. One is downward, other is upward. So this is the Kirchhoff law in loop 2. So it is equals to 0. Now simplifying. Open the bracket and minus term taken along the right hand side. I2 taken as common. I2 is a function of S. You know what is S? It is J omega, because I2 changes with omega. I2 is a function of the frequency. So VBE2 by Ohm's law, the impedance into the current. So as according to convention, the minus sign is applied. The voltage gain is VBE2 upon VBE1. Substituting I2 here, VBE2 here. So voltage gain becomes So this is the expression for the voltage gain. Now next we are multiplying HIE plus RL in numerator and in the denominator. It make no difference. Multiplying and dividing by the same term. Again simplifying. Now we are going to define the low frequency F1 as a particular frequency F1 by this value. This is the lead. With this, what happened? Substituting above, voltage gain, which is a function of S mean J omega, mean the voltage gain is a function of frequency. Here the J operator is coming, and this is mid frequency gain. You watch my previous video for the calculation of mid frequency gain. So low frequency equals to the mid frequency gain into and the magnitude of this is the root of this is the total expression. Now let it is theta, perpendicular base hypotenuse, and tan theta becomes, and theta becomes Now there are two things very important. As the expression of the gain was there are the two extremes. Number one, if S is made 0, then voltage gain becomes 0. You know S is what? J omega. Second, if S is made equals to this value, then in denominator becomes 0. 1 over 0 is infinity. So voltage gain becomes infinite. With this S value, you know, the gain becomes infinite. Now if we let F equals to F1, voltage gain at the low frequency becomes 1 over root 2 times the voltage gain at the mid frequency. This is the definition of low frequency F2. That F2 is the low frequency pass band.